Have you ever wondered how the tiniest particles can have the greatest impact? Welcome to the fascinating realm of quantum dots, where size isn't just about how big or small something is. It's a world where larger, uniform nanoparticles offer more space for electron waves, influencing their optical characteristics in ways that are really quite remarkable. But it's not just about size. These nanoscopic entities, these quantum dots, they exhibit behaviors that are nothing short of intriguing. When subatomic particles are confined within these nanoparticles, we see observable quantized effects. These effects dramatically shape their optical manifestations, turning them into a powerful tool for understanding the world around us. But what's truly exciting is that we're just scratching the surface here. There's so much more to explore, to understand, because in the world of quantum dots, size isn't just a measure of space. It's a gateway to a whole new perspective. Size, it seems, is more than just a measure of space when it comes to quantum dots. Let's dive into the deep end of quantum chemistry, shall we? When we talk about quantum dots, we're dealing with a fascinating interplay of principles that govern the quantum world. One such principle that's front and center is Heisenberg's uncertainty principle. Heisenberg's principle tells us that we can't know the position and momentum of a particle with perfect accuracy. The more precisely we try to measure one, the less precisely we can know the other. This principle is a cornerstone of quantum mechanics and has profound implications for our understanding of quantum dots. Now let's talk about size. In the quantum realm, size isn't just a measure of how big or small something is, it's a mathematical expression of position across a dimension or multiple dimensions. When we talk about the size of quantum dots, we're actually talking about the confinement of subatomic particles within a nanoscopic space. The smaller the quantum dot, the greater the confinement, and the more pronounced the quantum effects become. Quantum dots, these nanoscopic entities, are unique because their properties change with their size. Larger quantum dots offer more room for electron waves, which influences their optical characteristics. But it's not just about size. The way these particles are confined also influences their properties, leading to observable quantized effects. In essence, these foundational principles of quantum chemistry, like Heisenberg's uncertainty principle and the role of size and confinement, help us understand the intriguing world of quantum dots. They allow us to predict how quantum dots will behave and how their properties will change based on their size and the degree of particle confinement. These principles lay the foundation for understanding the intriguing world of quantum dots. But that's just the beginning. There's so much more to explore in the quantum world, and we're just scratching the surface. So buckle up, because we're about to venture deeper into the quantum realm. But what happens when we look beyond the size of these nanoparticles? What role does momentum play? Let's embark on an exploration of how the intrinsic and resultant momentum of quantum dots might impact their optical and temperature properties. The world of quantum dots is a world of fascinating possibilities. In this world, size isn't the only variable that has a significant impact. Momentum, too, can play a vital role, and the implications of this are far-reaching. Imagine, for a moment, a quantum dot. It's not just a particle, it's a dynamo. Its intrinsic momentum is the measure of its motion, the sum of its mass and velocity. Now consider the resultant momentum. This is the total momentum of a system of particles, considering both their individual momenta and the interactions between them. What happens when we introduce quantized light into this picture? The light, with its packets of energy called photons, interacts with the quantum dots, altering their momentum. This can lead to changes in their behavior, influencing their optical and temperature properties. This interaction could potentially give rise to a spectrum of radiation with tuned multi-components. With the right tuning, we could adjust the properties of the emitted light, leading to new possibilities in photonics and optoelectronics. Moreover, by understanding how quantum dots' momenta affect their absorption of quantized light, we could potentially improve our control over this process. This could have significant implications for applications such as solar cells, where efficient light absorption is crucial. Now, let's take this a step further. If we can understand and control the momentum of quantum dots, could we tailor this to meet specific needs? Could we design quantum dots with specific momenta to serve in diverse research and clinical settings, the possibilities are intriguing. The momentum of quantum dots, their intrinsic dance with light and energy, could open up new avenues for research and practical applications. This is more than just a new perspective on quantum dots. It's a perspective that could redefine how we understand and utilize these remarkable particles. The momentum of quantum dots could open up new avenues for research and practical applications. It's time to reframe our understanding of quantum dots and their potential applications. Historically, we've focused on the size and position of these nanoparticles, but there's an unexplored terrain here. Imagine the possibilities if we were to consider how quantum dots adjust their behavior in the context of quantized light when possessing an intrinsic or resultant momentum. Rather than being confined by the lens of size and position, let's venture into the dynamic world of momentum. This new perspective could offer a fresh approach to understanding the optical and temperature properties of quantum dots, potentially leading to tuned multi-component radiation. By focusing on the intrinsic and resultant momenta, we might even be able to manipulate the quantized light absorption of these particles, tailoring them to meet diverse research and clinical needs. As we push the boundaries of our understanding, who knows what new discoveries await in the realm of quantum dots? So what have we learned about quantum dots today? We've delved into the realm of quantum dots, exploring their size-dependent optical properties. We've discovered that larger nanoparticles offer more room for electron waves, impacting their optical characteristics, while the confinement of subatomic particles within nanoparticles leads to observable quantized effects. We've also pondered the foundational principles of quantum chemistry, with a special focus on Heisenberg's uncertainty principle and its implications on the momentum and position of entities at the quantum scale. We've dared to think beyond size and position, contemplating the role of intrinsic and resultant momentum and the potential effects on optical and temperature properties. We've asked probing questions, considering the possibilities of a radiation spectrum with tuned multi-components, and pondered how an understanding of quantized light absorption could be tailored to meet diverse research and clinical needs. The world of quantum dots is complex and fascinating, and we've only just begun to scratch the surface.